If you have equation, you are interested in the solution, right? And the differential equation is quite simple. You can easily identify the corresponding solution is nothing but this. Exponential decay function, e to the minus t over tau 0. Tau 0 is your cavity lifetime, times e to the jn times frequency difference times t. So this means an oscillation term, right? So, but this is a complex function. If you take the real part, you can get the electric field, which is depicted as the blue oscillation curve. It exhibits the so-called damped oscillation behavior over time, but actually over round trips. Remember, our analysis only accounts for the change in integral multiple of round trips. We do not deal with what happens within one round trip, right? 我们的模型只考虑一整个 round trip 发生了什么事，我们没有考虑在一个 round trip 之内的 detail, right? 所以我虽然画出来的这个 curve 是时间轴的 curve， 那实际上它的横轴代表的是整数个 round trip， 第一 round trip， 第二 round trip, okay? And the solution tells us your phasor, electric field, will oscillate with round trips, and the amplitude should decay with round trips. Okay. And with this curve, we can illustrate what are the meanings of the cavity lifetime and the frequency difference. According to the first term, we know what is tau 0. When your envelope decays from 100% to e to the minus L, e to the minus 1, the time you need is the cavity lifetime, tau 0. Okay, so longer tau 0 means the envelope decays slower because of the smaller cavity loss, which is reasonable. And secondly, the fringe density depends on this term, right? The green part, n times delta omega minus m. So it means your fringe density is higher if either your mole number n is bigger or your frequency detuning factor delta is larger. Okay? If you have larger n, your oscillation frequency is higher, so the period is shorter. Similarly, if your frequency difference, delta omega minus omega m, is bigger, you have denser fringes, shorter period. Okay. So this slide only tells you the solution to your electric field phasor of some arbitrary pulse mode should oscillate, damped oscillation, exhibits damped oscillation, and which factors determines your decay, which factor determines your fringe density. Okay, that's the purpose. Now, we move on to the second element, the gain medium. So we have known the complex amplitude of the nth pulse mode will become this one after one round trip due to the gain medium. So you can see the contribution from the gain medium is simply e to the g of omega n, which is easy, right? The only difference is previously we have to deal with a gain spectrum, g of omega, which is a curve. Now, we focus on a single pulse mode. So we have a single frequency only, right? So you just substitute omega by omega n. It's a number, it's no longer a function. But what is g of omega n, okay? We have to assume g of omega n is much less than 1. That means in one round trip, although you have some gain, but the gain is not strong. It's a weak gain, okay? Then the same approximation can be used. En prime previously is equal to En times e to the g, but since g is very small, so it can be approximated by 1 plus g, the same approximation, Taylor series approximation, to the first order only. Rearrangement, you got this. Do the same thing as before, you arrive at a new differential equation, the rate equation. But this time it takes account of the gain medium only. Okay? So the red circle highlights the contribution from the gain medium. Then you have to combine with the previous rate equation, which takes the cavity into account. Okay, remember previously you have something like this. The left-hand side equals 0 is your old rate equation. But in the presence of the gain median, you have to add g of omega n over big T times En to the right-hand side of your equality. Then you got a new rate equation. This time, equation 2 takes into account of two mechanisms, cavity and the gain medium together. Okay? 这个逻辑可以接受吗？没有 gain medium， 只有 cavity， 你得到的 equation 1是等号为0嘛？那我已经分析给你看，如果只考虑 gain medium 是微分要等于这一项，所以把两个 effect 要一起考虑，只要把它加到等号的右边就可以了。这 equation 2就同时考虑了 cavity and gain medium。Okay? But we prefer further approximation, further simplification. Here we assume the pulse bandwidth is much narrower than the gain bandwidth as we defined in section 2-1. So your G originally is modeled by a complex Lorentzian function, now can be approximated by second order Taylor series approximation. But in our case, we focus on a spatial case, omega equals omega n. We focus on the nth pulse mode. So the frequency is a number, omega n. In this case, your omega tilt in your model, you see omega tilt here and here, right? What is the corresponding number? Remember, omega tilt means frequency detuning, the absolute frequency minus the carrier frequency. Your absolute frequency is omega n, your carrier frequency is omega 0, but you already know their difference is nothing but n times omega n. 第 n 个 mode 的频率跟载波频率之间的差距，不就是 n 倍的 modulation frequency 吗？这就是它为什么被叫做第 n 个 mode 的原因嘛，对不对？ So whenever you see omega tilt, this time you only substitute n times omega n is okay. So g of omega n becomes this one. Okay? And if you substitute g of omega n into equation 2 derived in the previous page, you got this. It's equation 2 prime, okay, after approximation. And then you see the three terms go to here. The first term, const term, is here. The second term goes to here. The third term goes to here. Okay? So there are a lot of terms in equation 2 prime because g of omega n corresponds to 3 terms. So that's your updated equation. But to this point, there is no coupling yet, right? En is dependent on En itself. The nth mode depends on itself only. independent of other modes, right? You see unknown En only. You do not see any En plus 1 or En minus 1. So there is no more coupling yet. Until, before we move on, I can show you the meaning of each term. What is delta? It means frequency detuning. Your modulation frequency is different from your mode spacing. Then delta is non-zero. The second term actually means gain-induced dispersion. So what does this mean? It means the delay increment we have seen in previous section. Remember that our G, the gain spectrum, the imaginary part, can be approximated by a line with some slope. And the slope corresponds to a delay increment. The same thing is characterized by this term here. Okay? This one means the linear loss and the gain spectral peak because of L and the G parameters. And the last term means the curvature of gain spectrum because it comes from here. The second order term of your gain spectral coefficient. So what does the second order term mean? It means the curvature, right? So each term has its own meaning. Okay, here I offer another bonus question. If you stop here, you have already considered the contributions from the cavity and the gain medium, right? And if we focus on a spatial case when n equals 0, okay, what is n equals 0? Your central mode, carrier frequency mode. What is the solution? Exponential function? Can you justify? When n equals 0, what terms can you drop? This term can drop because when n equals 0, the entire term is no longer useful. Drop. What else? This term can be dropped. So how many terms do you still have? You have time derivative plus something like this times En itself equals 0. And what is the corresponding solution? Should be an exponential function. Either decay or growing depends on positive or negative of this term, right? But what do you expect about L minus G? What do you expect? What's the number, L minus G? 0, right? In theory, it's 0, right? So if it is 0, this term drops as well. So you have time derivative equals 0. What's the solution? Constant. And is it reasonable? It's very reasonable because now we are talking about CW lasers, right? Up to now, we only consider gain medium, the cavity effect, no modulator. If there is no modulator, you go back to the CW laser. So the solution should be CW laser solution, and it's a constant, which is consistent, right? How about when n equals 1? Again, it's a CW laser model, right? No modulator, so it's still CW laser. But what's the solution when n equals 1? Now you can no longer drop this one, you can no longer drop this one. But essentially, it's still a well-known differential equation. You have what kind of solution? should be something similar to what I depicted before, damped oscillation, right? And is it reasonable? Remember, this rate equation takes into account the dynamics, not only steady state, right? And the damped oscillation is it a reasonable solution about the CW laser dynamics? It's reasonable because it simply says whenever your n is no longer 0, say 1, 2, 3, 4, or whatever, your dynamics is maybe initially you have something, but in the end, if time is long enough, they will all die off because of exponential decay. So in steady state, they cannot exist. Only n equals 0 can exist. And that is the single mode CW laser behavior, right? So you can use this approach to review whether this model is reasonable. It seems that very consistent. Yes, your question.
How can we guarantee that it will die off after the time is long enough?
Because of the, if you have non-zero term here, your solution will have a decay term, just like what I depicted before, right? If you have decay term, then it's a matter of time, but in the end, it will die off. Okay. And only the central mode, this term disappears, this term is 0, so there is 0 decay, it can survive. That's a special case. Okay. Great. Your student ID? Yes?
CW 雷射的解的话，不应该是一个赛或口赛吗？那它的微分应该还是会是赛或口赛，为什么会是？
Oh no, here I solved the phasor, right? En is the phasor. So if En is a constant, you have a carrier term there. So you are right, in steady state it's a sinusoidal function. But here we only solve the phasor. Now, finally, we can deal with the modulator, and all the interesting things happen here, okay? The complex field becomes a new one, E prime equals E times the transmission function, eta of t, okay? We also have to assume the modulation depth is quite small, so delta m parameter is much less than 1. Then e to the delta can be approximated by 1 plus delta, as we used many times before. And the transmission function in our model is like this, the original one. But after this approximation, it becomes 1 minus delta m constant plus delta m times cosine omega mt. Okay, you just move the exponent here. That's it, using this approximation. But we also know cosine omega mt can be rewritten as 1 over 2 times e to the j omega mt plus e to the minus j omega mt, which I'm sure you have been familiar with. So now we have a different approximation compared with section 2-1. Okay. In section 2-1, we use Gaussian approximation. So eta of t is approximated by a Gaussian, shown by the green curve in this figure. And this approximation is valid for short pulse width. That means if your delta t pulse width is much smaller than the modulation period, this approximation is valid. If your pulse width is broad, this approximation is not good. But it doesn't matter your modulation depth, delta m is big or small. for the green one. Okay, that's what we used before. Now we use a different approximation, so-called raised cosine function. Eta of t is equal to 1 minus delta m plus delta m cosine omega mt, represented by red dashed curve. This approximation is different from the green one. It is valid for weak modulation only. So if the modulation depth is too large, this approximation is not good. As you can see, the value is different from the true value represented by the blue curve, right? And if your modulation depth is stronger, the error becomes larger. Then this approximation becomes less useful. But it doesn't matter whether your pulse width is broad or narrow, okay? So I compare the two approximations. Sometimes Gaussian is better, but sometimes raised cosine is better. Here we use raised cosine approximation. And you have to remember it is true only if modulation depth is small, which we have assumed. But it doesn't matter your pulse width is broad or shorter. Okay? Remember in dynamics, initially our pulse width is quite broad. So the red curve is still okay. But the green one is not good. It only applies to steady state pulse when the pulse width is very short. 好，所以简单用中文说一次啊，我现在已经使用过2种近视，各有优点。红色是我现在要用的，它的优点是脉冲不管宽还是窄都适用。所以 initial condition 的脉冲还很宽，它已经可以用了。它的缺点是 modulation depth 如果太深，它的误差就很大，就像我画的图。蓝色的 valley 跟红色的 valley 已经有一些误差了。那如果原始的 modulation depth 更深，这个误差就更严重。所以我们必须限制在 weak modulation depth 这个 approximation 才适用。那另外一个 approximation 是 Gaussian approximation， 它这个 depth 的误差不大，但是它只能适用在窄脉冲。那 initial condition pulse width 很宽，它就不适用。不过我们过去用它是用在 steady state analysis。At that time, pulse width is already short, so it doesn't matter. 过去用这个 green one, Gaussian approximation. Here we use the red one. Okay. So if we use the raised cosine approximation, what is the modeling? The output field is equal to input field times transmission. This is output field. Superposition of pulse modes. En prime means the phasor of the nth pulse mode after the modulator. Okay? And this one means original E of t, the input field. And the eta of t is represented by this raised cosine approximation. Okay? So what do you have? This one, which is an infinite series, times the first two terms, 1 minus delta m, is still this very similar infinite series. But when the infinite series multiply with the third term, the last term, something interesting happens. You can see omega nt times omega mt, right? You have to combine them together. So in theory, you have omega n plus omega m. Your new frequency is omega n plus omega m. But in reality, omega n plus omega m is simply omega n plus 1. Is it okay for you? 你就多加了一个 modulation frequency， 那不就是你旁边那个 mode 的 mode frequency 了吗？每一个 mode 的间距就是一个 omega m， 对不对？ For the same reason, omega m times minus omega mt, what do you have? You have omega n minus 1. So you are looking at the left-hand side mode. So you can easily write down this is your product. And you have already sensed now there is coupling. Because now the nth mode is no longer independent from other modes. At least it's dependent on the two neighboring modes, n plus 1 and n minus 1. But it comes from this relation due to the modulator. Without modulator, there is no coupling. With the modulator, you have coupling. Okay? Or maybe we can take a rest of 10 minutes. Then we can check what is the corresponding rate equation and what would be the solutions.